Hello everyone. So today I will present our work titled From Detection to Anticipation, Online Understanding of Struggle Across Various Tasks and Activities. In this work, we move beyond offline analysis and study how to detect and anticipate struggle in real time across diverse tasks and activities. My name is Jeff Wong from the University of Bristol. The struggle can be understood as observable difficulty in completing an activity. It is characterized by motor hesitation, repeated attempts, prolonged actions, frustration-related gestures such as hand or head movements, and disruptive errors or pauses. In this work, we move beyond traditional offline analysis, which assumes access to the full video. Instead, we reformulate the problem as causal real-time prediction using only partial observations, building on the EVO struggle dataset. By focusing on universal behavioral cues like motor hesitation, we make cross-task generalization feasible. Imagine a system that can predict frustration up to 2 seconds in advance. Our baseline models achieve around 70 to 80% accuracy while operating at real-time speed, approximately 20 FPS. So our work is based on EVO struggle dataset featuring struggle moments across 18 tasks within 4 activities with a particular emphasis on skill evolution over time. So here are some examples of how struggle appears in the EVO struggle dataset. Struggle often manifests as hand hesitation during task execution as seen in the tying knots and origami. So it can also appear as repeated attempts, such as trying different combinations in the tangram activity, or as motor errors like dropping cards during the card shuffling process, as you can see. Yeah. So this slide defines our problem. We propose a unified online framework for both real-time struggle detection and anticipation. At time step T, the model only observes past and current features and predicts whether struggle occurs at or after T. Trading is strictly causal, using no future information. In the figure, blue represents long-term memory, green short-term context, orange the anticipated future, and T marks the current decision point. So now let's move to our method. We adapt 2 strong temporal models for online struggle detection and anticipation. First, LSTR, the long short-term transformer, excels at capturing very long-range dependencies. It compresses history into a compact long-term memory, then uses recent short-term features as queries to attend to that memory, all while staying strictly causal. So second, we propose using CMERGE, the context-enhanced memory refined transformer, built on LSTR's memory setup. CMERGE adds near future feature prediction as an auxiliary task and uses a refinement module to improve the boundary accuracy. So we focus on within activity evaluation, training and testing on the same activity. We compare 2 approaches, separate models per activity. So tying knots, origami, tangram, shuffle cards, and 1 joint model trained across all 4, evaluated both pooled and per activity. We also test generalization to unseen activities or tasks, evaluate anticipation horizons, analyze runtime for real-time use, and show qualitative prediction examples. A random baseline around 50% CAP anchors our results, given the imbalance in the struggle occurrence. So now let's talk about how we evaluated our models. So we use calibrated average precision or CAP. as our main per frame metric. It's much more reliable than standard MAP in balanced settings with a random baseline around 50%. We apply it to both online decision detection and 2-second anticipation. For deeper insight, we add event level metrics, average F1 at IOU thresholds 0.1, 0.3, and 0.5. We also report expected calibration error, meaning predictions are trustworthy, and latency, anticipation lead time, and detection delay. So these are our key within activity results in CAP for online detection and 2-second anticipation. Both LSTR and CMERGE far outperformed the random baseline, proving they learn generating struggle signals. CMERGE is the clear winner, especially strong in origami up to 83% detection, beating LSTR by around 8%, with smaller but consistent gains in other activities. Detection generally scores a bit higher than anticipation, which is expected since predicting the future is tougher with possible sudden behavior shifts. Joint training across all activities holds up very well, only a minor drop compared to individual training, despite the added diversity. Moving to additional metrics with CMERGE and slow-fast features, frame level predictions are well calibrated. ECE stays low around 0.1. Event level F1 scores range from 0.37 to 0.58 across activities, with very similar results for anticipation and detection. Event level ECE is higher, 0.3 to 0.4, likely because grouping frames into segments adds some uncertainty. So most importantly, anticipation gives a solid 1 to 2 second lead time before struggle on site. Detection delay stays under 1 second, so the model responds quickly in real-time streaming. We conduct additional experiments to evaluate whether the struggle patterns generalize across different domains under the new online detection and anticipation settings. So there are two settings in the generalization experiments. First, activity level generalization. So training on 3 activities and evaluating on a completely unseen 4th activity with no prior knowledge of it. As figure 3 shows, the CAP scores drop compared to within activity training, but still clearly beat the random baseline, proving the model learns transferable struggle patterns across activities, though activity-specific data helps most. The second is the task level generalization, training on all but one task within an activity, then testing on the held out task. Figure 5 reveals that task-specific knowledge matters. Performance here is noticeably higher than in the activity level fully unseen activity case. So this confirms that familiarity with other tasks in the same activity boosts detection and anticipation significantly. So we also explore a stricter form of activity level generalization, what we called cross-activity or zero-shot generalization. Here, models trained solely on one activity are directly tested on the other 3 completely unseen activities. So the heat maps in the figures show the CAP scores for online detection on the left and anticipation on the right. Next, we examine the impact of skill evolution on model performance. We found that calibrated average precision CAP drops consistently when models are trained on later attempts as participants become more skilled. So moving to a runtime analysis, we benchmarked our online struggle detection and anticipation pipeline by using 2 video backbones, the slow-fast and the lighter S3D, paired with LSTR and CMERGE temporal model. All tests ran on a single 1080 Ti GPU with batch size 1. So as shown in the top table, CMERGE adds only a modest overhead. while the S3D with CMERT hits around 20 FPS still comfortably real time. The bottom table further explores the trade-off with feature stride and backbone choice. Here are some qualitative results of our experiments. We visualize the predicted probabilities of struggle and background to assess the model performance. So this figure shows predictions of the CMERT across 4 activities, where highlighted regions indicate that predicted struggle probability exceeds the background. So in conclusion, online struggle detection and anticipation work reliably up to 2 seconds ahead, with CMERS showing the best performance on both tasks and strong generalization. The system runs in real time at around 20 FPS. Next, we will focusing on the simplifying the model and refining the end-to-end pipeline for even higher accuracy in a lightweight system. So thank you for your attention.